Hi everybody. Today we will solve an electric field example. In this example we have two charges, okay, located on the x-axis. Q1 is minus 50 microcoulomb, Q2 is here plus 50 microcoulomb, and we are supposed to find the electric field here at point A and electric field right above the center, okay, between the two charges. So we would like to find out what is the electric field A and what is the electric field at point B. Okay, so let's handle the first one. Since this is an equilateral triangle, we can connect these two sides. And these distances are given actually in the problem. This is 26 centimeters and this is 26 centimeter. And this is 40. And this is also 40, of course, the same. And also, they give this distance to make the problem simpler. So the distance from here is 60 centimeters. And height of these two points is 30 centimeters. Okay, the distance and everything is given. We would like to find out the electric field at this point. As you see, at each of these points, the electric field has two components, one from Q1 and the other from Q2. The very first thing that you have to do in such problems is to find out the directions of these electric fields. Okay, the first one for Q1, because this is a negative, okay, the electric field will be towards itself through these lines. Not only through these lines, but like that, right? All the electric fields will be towards this charge. So that the electric field at point B will be this way. Okay, so this is E1. E1, of course, for point B. So this is E1 vector. And what about this? What about this side? This is also going to be like that. So this is also due to E1. Okay, good. Having determined the directions of, okay, each charges, then the problem will be easier to solve. For the second one, because this is plus, the electric fields will be away from these charges like that. And then obviously this will give you an electric field this way. Say this is E2, okay? Put the vector sign always, and here it will be also away, right, like that. So this is E2. Now the vector combination of these two will give you the result electric field. This is simpler because the length of these electric fields are going to be the same, because not only the charges but also the distances are the same, because this is equilateral triangle, so that the electric field at point B will be totally in x direction. So this is going to be totally in x direction. Okay, what about this one? This one, again, because we have two vectors, okay, so we can just combine them like that, okay, and then we will see that the resulting vector will be looking something like this, okay. So these are the total electric fields at these 2 points. As you see, each electric field has two components because we have two charges. So we have to find out the electric field, okay? The electric field at point B is simple, okay? Simple, because we have now, if we can calculate E1 and E2, which is exactly the same for this one, for case B, let's say, for case B, E1 magnitude is equal to E2 magnitude for this one, because we have the same distances, same charges. So if we can find one of them, it will be enough. So it's K, which is 9 times 10 to the 9, times charge, which is 50 times 10 to the minus 6. Micro is 10 to the minus 6, divided by the distance square. Don't forget, this is in centimeters, so it's 0.4 square will be the result. Okay? So if you just do this product, you will see that the result will be equal to, 2.8 times 10 to the 6 Newton per coulomb. So this is the electric field. Electric field due to these charges. Because of the symmetry, okay? Because of the symmetry, don't forget this electric field is this one or that one. But actually, E total is this one, okay? In order to find E total, okay, you need to specify this angle theta. So that, now let's look what's happening at point B. At point B, we have E2 there and E1 there, okay, E1. This is our X and Y. As you see, each one of them have X and Y components. This is the Y component of E2. This is the Y component of E1, and they cancel each other because one is up, the other is down. Exactly the same thing. When you subtract, they will cancel each other. However, these two components, the X components, will be added so that we will have twice as much as the cosine of these electric fields. So the net electric field, the total electric field, for this case at point B, okay, will be equal to, I put the vector sign theta, by the way. Cosine theta is just 26 over 40, okay? Because of this, right? This angle is exactly the same as this one. One side is 26, the other is 40, like 26 and 40, okay? Cosine theta is this, just division this, and it is given as just 0.65. So by multiplying by 2 times this E1, or 2.8 times 10 to the 6 times cosine theta, which is 0.65. Okay, so Y2, because don't forget, one came from E1 and the other came from E2. It's 2 times. Okay, so E total at point P will be totally in X direction. Okay, so this is the resulting. Okay, so if this length is twice as much as longer, as you see. Okay, so this E total is given by this expression. So in number, E total at point B as vector is equal to, okay, just 2.8 times, 3.6 times 10 to the 6 Newton per Coulomb. I. Actually, when you write this in vector form, you don't need to write the dimension, okay? So it's just that. So this was easy. So point B was easy because it was a symmetrical problem, but this is not. But let's look at case A. At point A, we have these two vectors. Don't forget, these two vectors. This is Y, and this is our X. Now, this vector is only Y component, and we can easily find out the magnitude. However, this one has two components. One X, this one X component of this vector, and this is the Y component, which is negative. Don't forget, the Y component of this is negative. So these two will be added, and the only X component will be coming from this part. And obviously, the result will be given by this vector. Okay, this vector. The tip will be right there. Good. So this is the resulting vector at point A. Now, we will do this separately. See, this is E2 and this is E1. E2 has only Y component, and it's easy to calculate, but E1 has Y and X components. So if this is 30 degrees here, okay, if this is 30 degrees because of the geometry, okay, because of the geometry, it's the same, okay, it's the angle given, then we can find out this E1x as E1 times cosine theta, okay, E1 times cos. What is E1? E1 is the electric field due to this charge. And the distance is 0.6. Don't forget, it's 60 centimeters. So K times 9 times 10 to the 9 times 50 times 10 to the 6, okay, micro minus 6 divided by the distance, which is 0.6 squared. Okay, this is E1x times cosine theta. cosine 30, okay? Cosine 30. Cosine 30. As you see, cosine 30 is square root of 3 over 2, okay? Over 2. So the result is that the x component simply is just 1.1 times 10 to the 6 Newton per coulomb. Okay, no vector sign on the left, no vector sign. So we put the unit again. So this was easy to handle the x component. The y component is equal to, just now, it is obtained by multiplying sine theta, okay? So E1 times sine theta, if you just put sine 30, which is the half, it will give you just 2 point, okay? Wait a minute. 2.2, okay, the y component, 2.2 times 10 to the 6 Newton per coulomb. Okay, very good. So what about the E2? What about E2? For this one, don't forget, we are still doing case B. E2 is simply equal to K times, or just 9 times 10 to the 9 times the charge, which is 50 microcoulombs, divided by the distance, which is 0.3 square. So E2 is given by that. And it is just, the result is 6.6 times 10 to the 6 Newton per coulomb. Now let's write, after finding all these values, let's write these as vectors, okay? So E2 vector is just 6.6 times 10 to the 6 J, okay? J, because it's in positive y direction, but E1 has x component, which is given by this one, and it is in positive x direction. So it's just 1.1 times 10 to the 6 I, but the y component is negative, as you see, down there, minus, this is very important, minus 2.2 times 10 to the 6 Newton per coulomb. So this is J. As you see, you don't need to write any unit for these two. Now, the sum of these two vectors is going to be E total vector at point A, okay, which is equal to just E1 plus E2. So in order to add two vectors, you add x and y components separately. The first one has no x component, but the second one has also have both x and y components, so that the result will be just 1.1 times 10 to the 6 I. Now the subtraction of 2.2 from 6.6 gives you 4.4. 4.4 times 10 to the 6, 4.4, 10 to the 6 J. Okay, so this is the resulting vector at point A. Now, this can also be written as ET is equal to 1.1 I minus 4.4 J, everything multiplied by 10 to the 6. So this can also be done like that. So now, what is the magnitude of this E total B? Okay, here this was very simple because we know the direction and the magnitude is exactly the same. But for this one, to get the magnitude without the vector sign, as you see, when I don't put the vector sign, it means it's the magnitude. You have to take the square root of 1.1 square plus 4.4 square. Of course, this is 10 to the still 6. Okay, so it's there. So the result is then just 4.5 10 to the 6. E total B is 4.5 times 10 to the 6, okay, Newton per coulomb. Now I'm writing the unit because it's not the vector, as you see. But when you write the vectors, you don't put any unit. Don't forget, this is something that we do in physics. Okay, so this is the end of the story. So I will continue, but before continuation, I will just stop recording and then let you ask me some questions.